Good morning. Pleasure to be here. Nice to see all of you. We have a pretty full room today. So, my name is Olivier Parents. I'm a faculty of economics here at UC. And I'm here to present our first speaker of the day, Professor Mills, Jeffrey Mills, that is also a professor in economics. We're in the same departments. And he's been doing Bayesian statistics, Bayesian econometrics for the past 30 years? About.
Since 1985.
Since 1985. So, before all the advance of MCNC samplings, all these things, so he was only doing Bayesian econometrics before that time here. So it's a pleasure to see Professor Mills that has been conducting research beginning in applied macro, but then moved to more like treatment effect in the medical field, working a lot with the psychiatric doctor in psychiatry,
yeah,
and to using about Bayesian testing procedures and to give some different metro analysis, meta-analysis, okay, it's not my area. Meta-analysis using Bayesian approach. And so it's a pleasure to have Jeff today. So for like next 45 minutes, we're going to be talking about Bayesian data without tears. Tools for
without tears.
Yeah, so tools for particular application. Thanks, Jeff. Go ahead.
Yeah, back in the 80s, we go to a conference and they put the three Bayesians in a little closet off to the side. It's growing. Nobody wants to get too close to a Bayesian overseas. We get
safety first.
Okay, so popularity is growing dramatically. I'll use the microphone because my allergies are bad, so I tend to start growling and sound not really bad if I try and shout right now. It's talk too loudly, but this one goes to 2018. I've been working in the last, I guess, about a decade. I've doing a lot of work with a colleague in psychiatry, so in the medical field, and definitely there's a big growth in use of Bayesian methods in lots of fields. People are realizing there's a lot of benefits, especially with computer power now. Right? So the real benefits come to the fore with our ability to use all that computational power. Right? So frequentist methods have passed and largely still the present. I've been saying this since the 90s, Bayesian methods of the future, but I think we're getting to that future pretty fast. There's a really good book. If you don't get anything else in this talk, go read Clayton Bernoulli's Fallacy. Most of it's, at least the first few chapters and the last few chapters are very bedtime reading. It goes into some nitty-gritty sometimes. He talks all about the replication crisis in science and why we should be using Bayesian methods. It's a really good book. I've got a lot of slides on the why still. I can't avoid talking about the why. I've been trying to explain to people why they should use Bayesian methods for too long. But I really want to get to the how to do it, because that's how I learned too. I learned by doing, right? I didn't understand statistics when you first took it. If statistical inference is just a bunch of math, but then you go do it, and you get some data, and you get some numbers, and then the light bulb starts going off, right? So if you go do it a bit, then I think it makes sense. I'm using Julia. I think that's also one of the futures. There you go. I'm starting to learn Python. I was using MATLAB and didn't like a lot of the things about it, so I tried. And I use R a lot in class. All my students learn R because that's the present. And I discovered Julia as I was starting to learn Python, and it's very similar to Python, easy to code, easy to read the code, but it's fast, right? So it's got the benefits of performance and ease of use. That's why I use it, but you can do all this stuff in Python, R, any of those, MATLAB. Gen AI might make that irrelevant, right, to be user-friendly, because they can write the code for us in C++ or whatever horrible language you don't really want to write on that's very performant. But I've found these LLMs still require a lot of hand-holding. They'll give you code, but you still need to tweak it. There might be some errors. You have to shepherd it a bit, so we've still got a little ways to go. Okay, so try and be fast on the why. What is probabilistic statistics? It's moving from deterministic logic. If A is true, you're told A is true, then B is true, right? Or B is false. Moving to, if you know A is true, then that tells you something about whether B is more plausible or not. Right? So it's under uncertainty. You don't know if B is true, but it gives you information, you're the detective. is be more plausible or not, right? So the definition of probability is a degree of plausibility, not long-run frequency. Any proposition A can be assigned a degree of plausibility, nothing to do with random variables, doesn't have to be random, doesn't have to be a variable. In fact, most of the things we're interested in are constants. We're looking at parameters and models, things like that. Maybe the prediction for next year, that one number, a set of numbers. It's not about frequency, it's not about randomness, it's not anything like that. And all probabilities are conditional on the information set. Right? We draw all these diagrams in intro statistics, and we say, oh, probability A and B, and we don't condition on anything. But even in this simple case, they're all conditioned on the sample space, the S, right? The probability space. If I chop a piece off of that, all the probabilities change. So they're all conditional. And then we get to the crux of the matter. What's the difference between frequentist and Bayesian methods, right? So if we use the notation up the top there, probability of B given A, right? So anything to the right of the vertical line is what the information you have you're using, right? The conditioned information. So what do I know about B? What probabilities am I going to assign to B if A is true, if I know A is true? And the key is probability of B given A is not the same as the probability of A given B, right? The probability the Pope is a Catholic is not the same as probability some random Catholic you chose is the Pope, right? They're very different. But that's what we do when we use maximum likelihood in the standard frequentist methods. We have probability of the observed data, y, given our model parameter, right? And then we try and find a model parameter that maximizes that. We say, well, this parameter gives me the most likely probability that I observed the data I did. What we really want to know is what's the probability that that parameter, mu or whatever it is some particular value, right? What probabilities do I assign that it's 10 or between 8 and 12 or minus 50? So we really want the green, the probability of mu given y, not the probability of y given mu. So to do that, simple one equation, you need Bayes' rule, right? The blue is the probability of B given A, and everything else you've assumed, your model, all the assumptions in that, and so on. And what we want is the green on the left there, the probability of A given B, and all those assumptions. Well, to get that, you have to use Bayes' rule. You need the probability of A given A, right? And that's what we call the prior. So we need that. And that's just what we know probabilistically about A before we observe B, before we use the information to know B, right? And in inference, A is the model parameter we're interested in, or whatever quantities we're interested in, the prediction and so on. And B is the data. And we're going to do all this numerically. That's the beauty of all the computational power, right? So the big question you always get asked, and I've been asked this for decades, and I never know the answer, but I've finally come up with what I think is the right answer is, where everyone worries about where does the prior come from? What about the prior when they're trying to do Bayesian analysis? Prior is just what we know about the parameter or whatever it is we're interested in ahead of time, okay? All the real assumptions and information are in the likelihood. The likelihood is a very informative prior for the data, right? We pick a model, we pick a set of variables, we pick a distribution, and then all we do with the prior is, given all that, given our model, what's reasonable values for those parameters? Okay, that's all it is. It's nothing that complicated. It's the second order problem compared to picking the model. Oops, I'll have to do it this way. So uninformative priors are a nice, easy way to do that. What I like to call them alien priors. It's the uninformed alien. The spaceship crashes on the planet, and the windows are all broken. You can't see out. Most of the sensors don't work. You don't know what's going on, but you're getting some data, right? You're getting X's and Y's. You're getting numbers on some things. You can fit models. That's what we do when we do statistics a lot of times, right? We just get some data, and we act like we know nothing about that data. We say, okay, this variable is Y, and these are the X's, and I'm going to play around with that. We usually have a lot more information than that about those X's and Y's, their particular variables, but the uninformed alien prior is just put a uniform prior on everything. I got some mean, I don't know what it is. It's somewhere between plus and minus 10 million or something. We pick a white interval. It doesn't matter. And if you use a uniform prior, you're always getting your likelihood function back, because you're just multiplying. So if you look at the equation at the top here, if P of A given M right at the end there is a constant, because it's uniform, then that just goes in the normalizing constant. You're just getting your likelihood function back, right? So we can do exactly the same thing, only now we can compute probabilities, right? So that's one easy prior. There's a literature in there in textbooks that say, oh, you shouldn't use uniform priors, but I think the reason for that, and they don't want to tell you, is because Bayes factors are a problem. Okay? They want to be able to compute Bayes factors, and so they don't like uniform priors. But if you don't bother with Bayes factors, and I don't think you should bother with them, then you can use uniform priors, right? But any uninformative prior, you can just pick a normal distribution and make the variance very big, right? It's going to be very spread out. The next step is to go to weakly informative priors, what I like to call axiomatic priors, right? An axiom is a truth that is self-evident to any reasonable expert in the field, right? So hold these truths to be self-evident. If you're trying to predict sales of some product in a store, donut sales in a store, they're not going to be minus 1,000. That's impossible, right? And they're probably not going to be 10 million. So you can put an interval on that. If you're trying to do something with humans, we know a lot about humans. If you're trying to say something about human height, you know if humans not going to be minus 1 foot tall, you know they're not going to be over 20 feet tall. If the company raises the price of a cell phone by $1, that's not going to decrease sales by $10 million, nor increase it by $1 million, right? It's a small change in price. It's not going to have that much effect. We can use that information in a way that everybody can agree just by putting bounds, right? Put inequality constraints. And then you can go to informative priors. They can be very beneficial, but use them with caution, until the revolution is over and everybody's Bayesian at least, right? So for now, I would say, even if you're just using uninformative and weakly informative priors, there's lots of benefits. And there's very little controversy to be found in that, right? You can always impose inequality constraints. If you know a parameter or something has to be positive, then just use a truncated distribution. That's very easy to do using Bayesian methods. Much more difficult from a frequentist point of view. Patients in clinical trials. The work I've been doing, we look at trials of anxiety or depression. Usually the measures of those have very narrow ranges, right? We've got just 3 examples of measures we've used for anxiety, pediatric anxiety rating scale, excuse me, and so on, right? So PARS, QIDS, CGIS. PARS is between 0 and 25. It can't be bigger than 25, it can't be less than 0. Right? QIDS 0 to 27, CGIS 1 to 7. So why not use that information? Right? You look at all the standard mixed model for repeated measures everybody uses for these things, and they just treat those variables like they could be plus or minus infinity. Right? That's throwing out an awful lot of information. So we want to be able to do all this computational. Back in the 80s, we had to sit down with pen and paper and do it analytically, which is why nobody was a Bayesian. It was a lot of work, but now the computer does all the work for us. Because Stan Ullum is a mathematician at Los Alamos, and he got sick, and he was in the hospital, and he was playing solitaire, and he's a mathematician. So he tried to figure out the combinatorics, and was sitting there with pen and paper, sick in the hospital, trying to figure out what's the probability of success in a solitaire game. And he sort of got frustrated and tired, and then realized, I can just count. I don't have to do math. I can count how many times I win in a lot of games, and that's going to give me the answer. Lower large numbers, I'm going to converge on the answer. And you realize, oh, with a computer, they had ENIAC at Los Alamos, we can actually do this. So you rush back to Los Alamos, and the rest is history. They published the first unclassified paper, and they called it the Monte Carlo method because his uncle was a gambler and was always saying you have to go to Monte Carlo. So that's where the name came from. But they published these papers in chemistry journals and places where statisticians would never find them. Right? So it's unclassified, but it's hard to find. But that's the whole idea, right? So the Stan Ullum approach is Monte Carlo simulation, and we're using the law of large numbers, just in a different way from standard frequentist saying, okay, pretend we have a large sample. we've got a small sample, but we're going to make a lot of draws from the posterior. We're going to numerically use the law of large numbers to improve our approximation. Right? So the idea is you've got some unknown quantity, say a parameter, and you're going to get a lot of draws from that distribution of the parameter, and then you can plug those draws into any function, and you get the expected value of the function. So you can get the posterior distribution of any function. Right? And R is your number of draws. Iterations is not the actual sample, so you can make that numerical approximation very precise by taking a lot of draws, right? For a given, so D is your data for a given sample size. You may only have 10 observations, but you can get a very precise estimate of the small sample distribution of any function of the parameters then. So let's do a couple of examples. So you've got some, success or failure. Lots of situations of take the left door, take the right door, take the red pill, take the blue pill. Remission. Is the patient in remission or not in medical settings? They use CGIS a lot for that. If it's 2 or less, the patient's in remission in terms of anxiety or depression. Purchasing, does the customer purchase the product or not? Did you get some disorder or disease? Did you catch the flu? Did you get a side effect? What's the probability of getting a side effect for taking some treatment? Right? This shows up all the time. There's lots of examples. Success can actually be the failure, right? It could be death, right? But we end up with this binomial likelihood, right? That just comes straight from this. It's easy to derive. There's no real controversy there at all. So there's a likelihood function. It's the probability of S successes, number of successes, given your data and given this model. So there's only one parameter in this model, probability of success. The way we test with those models is, standard way is the Fisher exact test, which is actually not exact because this is a likelihood function, and S is discrete. You can't have 1.5 trials, 1.5 successes. It's 1, then 2, then 3, then 4. So the p-value jumps. Every time you change S, it's going to jump because of that discrete jump, right? The other way to do that, to avoid that, is to do a chi-square test, but that's asymptotic, right? So that's large sample. That's assuming you have a big sample. It turns out the Bayesian exact small sample inference is easy. We've got a binomial likelihood here, and we just got to multiply it by a prior. Well, the alien prior is, okay, the only thing I know is logically, theta's a probability has got to be between 0 and 1. 0% to 100%, 0 to 1. All right, so if that's the only information I have, uniform distribution. It's anywhere equally likely to between 0 and 1. It turns out the beta distribution with parameters 1 and 1 is exactly the uniform. So it's just another way to write the uniform. And it turns out if you write it that way and multiply it, so you actually do the pen and paper math in this case, it's not complicated. You end up with the posterior distribution using Bayes' rule is also a beta distribution. It's just S plus 1, n minus S plus 1 in the parameters. So all we need a number of successes, number of trials, and a beta distribution. Right? And how to draw from a beta distribution, that's easy. So we've got a posterior distribution. I'm not even going to try and do anything analytically or plot it using the PDF or anything. I just want to be able to randomly draw from that distribution. So I randomly draw a lot of draws. Here's drawing 1 million draws from a beta distribution. I use Julia, but as you'll see, the code is doesn't really matter what you use. It's just very clean and easy to read, right? I've got an example here where there's 10 successes in 36 trials, so 10 outcomes of something. And I'm just going to draw 1 million values from that distribution. Plot them, calculate the 95% interval. This is a probability interval now, not a confidence interval. There's no weird interpretation. It's the interpretation everybody makes of a confidence interval that's wrong, right? I'm taking into account all the small sample properties here, and you just do summary statistics, right? So what I mean by Bayesian data analysis without tiers is that if you can do summary statistics and plot things, the computer does all the rest of the work. Right? So all you have to do is plug in your distributions, and we don't even need to come up with the posterior, as we'll see. You just need your likelihood, so your model and the distribution. Come up with some reasonable priors that can be uninformative, so you can put uniform on everything, that's fine. And let the computer do all the work and just do summary statistics. I use the same same example in Python and R. I don't even use Python, haven't used it in a long time. I use R in class, but I just put it into Copilot. I'm an economist, so I'm cheap. So, Copilot's free at UC, so I'm using the free version. I keep meaning that I've got to get myself a paid subscription to something good. So, it does a pretty good job. You have to tweak the code a little bit. You do, it's like an intelligent assistant, but it does make mistakes. So our jobs are still safe. We still have to shepherd the code and check it and make sure it runs and does what we want. But you can see they're all just doing the same thing, right? Random draw from some distribution. You can draw a million draws on your laptop like that nowadays. If I tried to run this back in the 90s, it would have used my computer for a month. Very easy to do this, right? It's just get the Monte Carlo sample, do some summary statistics. So here's an example doing exactly that. This is a child-adolescent anxiety multimodal study, CAMS. So looking at different treatments for anxiety in children and adolescents. And the monotherapy is sertraline, so giving them the sertraline medication compared to placebo. Right? So you just get number of successes in number of patients in the sertraline group, number of successes in number of patients in the placebo. There's a big placebo effect in anxiety, depression, a lot of these trials, but especially in psychiatry, there's a big placebo effect. The mental health system in the US is horrible, right? So if you're suffering from anxiety or depression, you finally get in to see a trained psychiatrist who's going to treat you, you already feel better, right? And at the end of the trial, even if I'm getting a placebo, if I can hang in there, then they're going to treat me. If I get worse, they'll pull you out of the trial and treat you, right? So you get this big placebo effect. So the question is the drug treatment actually doing any better than just, okay, they're going to feel better anyway, so you need the difference, right? But it's just using these beta distributions, the number of patients that reached remission out of the group, and we get these distributions. Now what we were interested in is the difference between those, right? Which is an analytically intractable problem. There's a paper, I found the most recent paper I found, I think it was 2019, and they went through about 10 pages of algebra, and then they did numerical integration at the end. It's just not analytically tractable. We can do this very simply, right? I get all these draws from this distribution. I just do this, draw from a beta, give me S and N, do the same for this group, I get those two. Now I just take the difference of the two draws, subtract the one set of draws from the other set of draws. And I get the posterior distribution for the difference. Small sample, exact distribution. Okay, there it is, and hypothesis testing. Right? There's a big crisis in statistics and science about hypothesis testing. Journal articles are all wringing their hands, and 50,000 statisticians are writing letters to the editor, all because p-values are horrible. Right? All we need to do is play where's Waldo. Where is zero in my distribution? No effect would be zero. Oh look, it's way out in the tail here. Right? Zero is over here somewhere, and then I can say, well, there's no statistical evidence of a difference. I can look at this, I can compute the area in the tail, the probability that zero or less. I can put a probability interval on there, or credible interval, or highest posterior density interval is the Bayesian version of a confidence interval. It's just the probability that the parameter is actually in that range, right? Then we do the same for another treatment, right? This is a combined treatment of sertraline plus cognitive behavioral therapy. You see that does better. A lot more people reach remission. The green is placebo again, that's the same. The scale's a little bit different because this is a more narrow distribution. And then we just take the difference of those draws, right? So all I have to do is get those two sets of simulations, take the difference of the draws, and I've got the posterior distribution, small sample, no large sample assumptions of the two treatments, okay? And then even better, what's really cool is now I can do the difference of the difference, okay? No fancy math required. I've got all the draws from this distribution, the yellow one, which is the difference between the combined therapy and placebo, and I've got all the draws from the purple, Louis purple distribution, I don't know what color you call that, between the monotherapy, sertraline and placebo. I take those two distributions, I take the difference of the draws from those, this is the distribution of the difference of the difference. very analytically intractable problem, trivial to do on the computer, and I can get all my summary statistics from that, be it, probabilities. Clearly that's greater than 0, right? So clearly the combined therapy is a lot better. Once again, visualization, right? Where's 0 on this distribution is way out in the tail. Clearly there's strong evidence that the combined therapy is better than monotherapy. Okay, we can do lots of other things with it. Meta-analyses, looking at the activations of side effects. We can look at side effects in different groups. I'm not going to spend too much. Let's talk about how to do it. Right, that's what we want to do. So what's the Bayesian machinery? We're going to use Markov chain Monte Carlo, okay, which is this process where all you need is the conditional distributions, which nowadays, we're going to use Stan or Turing.jl and Julia. They're both essentially the same thing. But what it does is you give it the likelihood and your priors, that's all you have to do, and it uses the likelihood and the priors to get the conditionals, because that's fairly trivial to do. So the computer can do that for us. And you draw from, so here we've got 2 parameters, A and B. So you pick a value for B, draw from A, distribution given B, then given that value of A, you draw from B, you get a new value for B, use that value for B to draw from A, and just keep going through this chain. Right? And that, under remarkably general conditions, that converges to draws from the distribution for B, given just the data, and the distribution A for just the data. Excuse me. So we get those Monte Carlo sample. It's not the data sample. It draws from these posterior distributions and just do summary statistics on it. Right? Standard stuff. Okay, so here's my workflow. Think about which model you want to use. Excuse me, write down the model. That's where the alien would fail miserably, right? You have to think about which variables I'm going to put in my model. Is it linear? Is it, do I need a log in here, or quadratic, or something else? Interaction terms. Should I be using a logit logistic, or a probit, or a multinomial logit, or a tobit, or something like that? Am I just doing differences in means or differences in proportions like we did before? Am I doing some kind of time series model or regressive integrated moving average, that kind of thing? Write down your model, you have to pick a distribution. The normal is a pretty safe assumption for the errors of these models, right? Because central limit theorem, maximum entropy principle, and so on. But we can use other distributions as well, very easily. We used the data just now. So you write down your model, pick priors. Your parameters, right? So, there's 2 parameters in this model, and this is 3 actually, because we could have a complex covariance matrix if we want. Yes, there may be some parameters in here. Here we've just got 2 parameters plus the variance parameters, different variances, standard errors. Here we've got these 3 parameters plus the standard error of the equation. Right? So you need priors for those parameters. As I said, uniform priors are fine. Just pick uniform priors and give them some reasonable range. If the range is too narrow, you can see that when you get the posteriors and go back and say, oh, I inadvertently made it too narrow. Or you can just pick normal priors with large variance. Those are good defaults. And you can always plot the prior with the posterior to check how informative the prior is. You can see, is it pretty flat over the range of the posterior, so it's having no influence, right? But use inequality constraints, right? We know a variance or standard deviation has to be positive. Why not use that to help get better estimates? And then, so that's all the hard work. The rest is done by the computer, right? Apply MCMC, or nowadays we use HMC. MCMC is like throwing dots at a dartboard, right? To get draws. HMC is like a guided missile. It's used in a lot of the physics of the process to automate everything. And what it does is you don't have to give it any tuning parameters or worry about any of that stuff. It does all the work for you. Okay, so that's what Stan in R and Python use Stan, named after Stanislaw Elm. And in Julia we use Turing.jl. And it uses the same syntax as STAN, because it's written after STAN by some people in Cambridge, England. It does the same thing. So Hamiltonian Monte Carlo, you give it the data, what your unknown parameters are, write a model statement. As we'll see, that's just, okay, state my priors and the model, and the link equation, run the algorithm, and step 4 is just do summary statistics, right? Plot the posterior density, compute means and standard errors, compute intervals, do some hypothesis testing. Where's 0, right? You can see 0's out in the tail here a bit. I compute the probability that phi is less than 0, 0.005. So obviously the probability that's greater than 0 is 0.995. Pretty strong evidence that it's not 0 here. And as we said, we can compare distributions. I can compare the distribution of the same parameter in 2 different models. Right? I could run another model with other variables in, get the posterior for that, and plot them and take the difference of those draws and get the distribution of the difference in parameters. Right? Something that's pretty tricky to do otherwise. As I've said, null hypothesis, NHST is null hypothesis significance testing. Right? It's very flawed. There's a lot of hand-wringing in the literature about that. So a lot of Bayesians run around saying, oh yeah, you can use Bayes factors. Well, you've heard of Occam's razor, right? That's where, simplify, get rid of unnecessary assumptions, keep it simple, stupid. There's also Occam's broom. That's where you sweep all the problems under the rug, you don't mention them, you publish journal articles. And I think that's going on with Bayes factors. There's some problems. I think that's seriously flawed too. But we don't need Bayes factors. I don't know why they're so tied to Bayes factors, maybe because their whole career it's institutional inertia as well. Right? It's like the QWERTY keyboard. Why do we use this horrible keyboard that was invented for those typewriters that curve things to slow you down? It's designed to slow you down, hurt your wrists and stuff. We're stuck using it. We don't have to be stuck using Bayes factors or NHST. We can visualize. Where's 0 on the line, or whatever value you're trying to test. We can compute intervals, probabilities. We compute odds against the null hypothesis, right? All odds against, let's back up, yeah. Odds against the null hypothesis is just, what's the most likely value? It's the same thing as the likelihood ratio, right? What's the most likely value? And if I use a uniform prior, then it really is just the same thing as the likelihood ratio. What's the height of the density at the most likely value? So somewhere here is like what? I don't know, 3.2, 3.3. And what's the height of the density at 0? Pretty small, right? So I'm going to get a big number if I form that ratio here. And we can do that easily. That's all you really need to do with those kinds of things. Okay, so some simple examples. Show you how to do it so you can go do it. You don't have to believe me. This is a Turing.jl model statement, but the STAN statement is very similar. This is a little bit cleaner so you can really see what's going on. There's some gobbledygook you put it over here to make it run faster and work, but you don't really need it, but you just always put it there and forget about it. That's why it's in purple. Just makes things work better. That's, Julian is the type system and object-oriented programming, all that stuff I know nothing about. We don't need to. It's really a functional programming language. But the way it's written uses this a lot. So suppose we have a simple regression. We've got 2 regression parameters, intercept and slope, and we've got an equation standard error, sigma. Okay, we could write that in matrix form. So you're just going to give it your data, y, a dependent variable, and your x variables in the matrix. Right? There's only going to be 2 columns in this model. I'm going to have ones for the intercept and the x values for the relationship between x and y. You get the b coefficient. Right? So size of x in this case is k is going to be 2. There's 2 parameters, and n is however many observations I have. So now I have to define some priors. So I'm just putting a uniform prior on sigma. And I could make this 0. I don't know why I made it 0.1, but some small number of 0, and then some pretty large number. If you think 10 is too small, make it 1,000. It doesn't matter. You can figure out once you plot the posterior where it should be, and it just speeds up how fast this runs if you don't give it values way out in none. So it's drawing from the prior out there, and it takes longer to find where it should be, right? Got a question?
Yeah, I just had a question to check my understanding. So for the priors line with the sig equals the uniform, it generates the number from the uniform distribution. So what, if you could go into deeper detail again for me, what is that line doing?
So that's just telling Turing, which is the HMC package, essentially, right, that, okay, I have some parameter that I'm calling sig. It's distributed as, so that's why we use this squiggly tilde instead of equals, right? It is distributed as a uniform distribution in the range 0.01 to 10. Right, so I'm just saying it's flat line between A and B, and I've said A at 0.01 and B at 10, and I can change those numbers.
So that's not generating a singular value, it's generating a distribution?
Yeah, it's saying this is the distribution you're going to draw from.
Okay.
Exactly. Thank you, yeah. And then I'm doing the same thing with each of the betas, right? So I've just put those in a vector and thinking of it in matrix terms, right? So beta 1 is A and beta 2 is B. So I've got two parameters, I'm just giving them both a normal. So these are distributed, it's a distribution, a normal, mean 0, standard error 20. So really wide distribution on these parameters. You can make that bigger if you thought beta might possibly be a large number, positive or negative, just make this really large. You could put a uniform here or whatever you like to. If you want to run a logistic, logit, whatever you want to call it, logit is just the inverse function of logistics. So econometricians call it logit model, statisticians call it logistic, it's the same model. If you want to do that instead, you just need this one line, right, and put in mu here instead of x times beta. And then here's my likelihood. So I'm just stepping through one observation at a time and saying my dependent variable, each observation is A plus bx, in matrix form, x times beta, x prime times beta, and the standard error of the equation is sigma, right, sig. And that's it. That's my model statement. So most of the work's done. So now you just estimate, right? So I call that function simple underscore regression, and I need to give it y and x. So I pass it y and x. I tell it how many iterations I want to do. 20,000 here. You don't need to do as many iterations with this as sort of unsupervised MCMC. So typically we don't have, 20,000 is quite a lot of draws, but it runs really fast. This is just a call to the no U-turn sampler, which is the HMC sampler, to do the MCMC, telling how many iterations, what model to use. Then you plot things, pull out the MCMC draws, and do some more plots, calculate a 95% interval, draw some lines on the graph, give me the interval, give me the mean, things like that, right? It's just all summary statistics at this point, right? So this is where the computer does all the work. You just come up with your model, and it does the estimation, and then you do summary statistics. So this is the kind of output you get. The plot CC, straight from the sample, gives you all this, right? So you can look at your MCMC sample and see it's a nice stationary chain that looks like it's converged well. That's all you're looking for is that kind of thing, something that looks like that. And here's my posterior distributions. Okay, the top one is sigma, I believe, but that's not, that got chopped off. But this is beta 1, my intercept, my alpha parameter, and this is beta 2, my slope p parameter, right? Standard errors. This is a measure of numerical accuracy, so you can see it's whether I should run it for longer. You can see it's pretty accurate. This is small numerical standard error on that, so I'm good at 3 decimal places at least. Lots of examples of how to do this. Just Google Stan user guide, and it comes up with this. I opened the first couple, like this is linear regression. You can see there's all these different models in here, logistic, probability, blah, 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 hierarchical models, time series models, missing data, and so on. And those are all just right there, and you can pretty much Google anything you want, and it's easy to find the model statements from either in Stan or Turing for Julia, and in Gen AI, you put it in Copilot or ChatGPT or something. If you've got it in Stan, I've done that. I've just copied the Stan code and said, I want to do it in Julia instead, and it'll convert it for you pretty well. So here's a somewhat more complicated example, and that's an ARIMA model. Right? This one is one that causes more problems for frequentist approach. right? It's a decent, intuitive approximation of human behavior. You do whatever you did last month, your income's whatever it was last month, you buy the same things at the grocery store, plus the error correction term, the same thing that shows up in error correction models and vector error correction models when you talk about co-integration. Just the idea that you look at your past mistakes or opportunities, if you like. So if you think about if you're self-employed, say, if you made a lot of money last month, you might step off the gas a little bit this month and play a bit more golf or whatever. Or if you got behind and you got bills to pay last month, you might work harder this month, right? Things like that. Or if you went to the store and something was on sale and you bought a lot of it, next month you're going to buy less of it, right? So this is the error adjusting for that correction, right? A simple model, but it's nonlinear because I got this parameter theta, which is unobservable, and I've got these the equation errors u, which are also unobservable, right? So that's just another parameter. So I've got t of these parameters. How many observations are n? So if I got n observations, I got n unknown parameters here, plus the theta and the phi and the a. The only thing that makes this work is this recursiveness in these residuals. Otherwise, you'd have too many parameters to estimate, right? Behaviors are often highly correlated over time, so phi is often close to 1. If it gets to 1, like in stock prices, random walk, then that's a problem from the frequentist approach. It doesn't matter from a Bayesian approach, this value can be anything. We don't care if the parameters larger than 1 or not, because all that matters is as long as the error term is stationary, the variable doesn't have to be. Whereas for a frequentist estimate, if you think about the OLS estimate, it has y in there, so in order for it to be stationary, y has to be stationary. And then the frequentist approach relies heavily on asymptotics. So large sample, assuming we have a large sample. We pretty much never have a large sample in time series because the old data is irrelevant, right? If I go get GDP from 1947 to 2022, how relevant is the data from the 40s and 50s? They're probably better off throwing it out, right? So we always have this small sample. Plus the data is correlated. So a new observation doesn't tell me that much. A new observation of GDP, is like 95% is, I already knew. I can predict GDP with like 98%, 99% accuracy just from knowing the previous value. Choose that as your estimate, right? So there's not much information in a new observation. So you need a lot of data. Okay, so we're always in this small sample world. And we don't want to be constrained by this having to be stationary. Yeah, we can difference, but that doesn't always work. So sometimes we want to model variables on stationary. We can do that in this set. Here's the standard ARIMA function in R, which is weird because they give you the mean. I don't know why they do that. So that throws people off when they try and forecast because this is the mean, it's not the estimate of A. It gives you the parameter, it just gives you asymptotic standard errors, no p-values or anything. You have to calculate your own confidence intervals, asymptotic symmetric intervals around these parameters. Let's do it instead. Oh, sorry, Julia, this is in Turin, but it's very similar to the same. All right, so all I have to do is, let's talk about the model first, specify the model, the likelihood, right? It's just our variable x, I've called it x instead of y now, sorry. So xt is just alpha plus phi xt minus 1 plus theta ut minus 1, right? So the autoregressive and moving average components. And then I'm just defining the current u. It's just xt minus this lot, right? So there's my model. And I got to start this off, right? Because I got this lag, xt minus 1. When x is 1, I don't have the previous value of x. So for my first observation, I've got to give it the simplified version, drop in all these terms. So that's my model statement in terms of the equation. And then I just got to put priors on my parameters. So I got the same uniform prior on sigma that we used before. Pretty uninformative priors, because I know these parameters are going to be fairly small for these. I could make this, I could put 300 in all here, and it wouldn't really make any difference at all. So uninformative priors. And here's what I get out of that. You can see the priors are uninformative just by looking at these standard errors. They call them standard deviation of the MCMC sample, that's what it is, but it's the standard error of the estimate. Okay. So if I look at my priors, 3, 2, 2, as my standard error for my prior, oops, wrong way, These are all orders of magnitude small, so a much narrower post-period distribution. So the prior is essentially flat over the range of this distribution, over the support of the distribution. What's interesting here is you see that